Hello everyone, welcome to our discussion video for the M4 Practice Hackathon. Today, my partner and I will discuss the feat of our best performing classifier, designed to predict the binary loan outcomes. Our overreaching objective was to maximize the F1 score on the test data, while ensuring the model is well fitted. We'll walk you through the iterations that got us to our final Kaggle submission. So to improve the performance of our classifier, we first focus on feature engineering. We use the polynomial features to combine numerical variables like applicant's income and the loan amount. This allows the model to discover deep, nonlinear interactions rather than just specific trends, which significantly improved prediction quality. Next, we compare three different models: the XGBoost, Random Forest, and Histogradient boosting. Random forests give us excellent variance reduction, while XGBoost yields the highest raw accuracy. However, XGBoost alone was prone to overfitting. We eventually combined all three into a calibrated voting ensemble to balance their strengths and weaknesses in terms of the F1 score and real-world business implications. So, to handle the class imbalance, we initially tried simple class weighting, but it was insufficient. We transitioned to using smooth/ENN. Unlike the standard smooth, the smooth/ENN generates synthetic samples for the minority class and actively removes the noisy overlaps between the classes, which created a crystal clear decision boundary. We also tuned hyperparameters using randomized search CV. By severely restricting the max depths and increasing the L1, L2 regularization, our model's performance on unseen data stabilized beautifully compared to the heavily overfitting pre-tuned phrase. So now, let's talk about how we assessed and improved the fit of our classifier. Instead of a simple train set split, we used stratified five-fold cross-validation. This validation strategy ensured performance stability by giving us an unbiased out-of-fold probability estimate across the entire dataset, preventing the data leakage. So, as shown in the graph, in predicted learning curve visualization, our initial XGBoost model was heavily overfitting. The training score was nearly 1.0, while the cross-validation score lagged far behind. To address this issue, we implemented aggressive dropout rates and strong regularization. This successfully brought the two curves closer together, demonstrating a well-fitted model that generalized well to new data. Looking at the confusion matrix and the precision recall curve, we analyze the critical model trade-off. In a loan approval setting, a false positive means rejecting a good customer, which costs the business potential interest revenue. A false negative means approving a loan that defaults, which costs the business the entire principal amount, a vastly higher financial risk. If applicable, to balance this risk and maximize the practical value, we dynamically adjust our decision threshold. Instead of relying on the default 0.05 cutoff, we utilized our cross-validation probabilities to lock in an optimal threshold that prioritizes reducing false negatives while preserving a high macro F1 score. So finally, if we had more time and resources to further improve the classifier, we would integrate an external dataset, such as macroeconomic trends like inflation rates or direct credit bureau data, which could significantly enhance the predictive accuracy. We would also propose a strategy for monitoring model performance in production. By tracking statistical distribution in features like annual income over time, we could detect the data drift early and automatically trigger model retraining to handle shifting economic conditions. Thank you for your time, and here's our result.